Welcome to Late Night History. Settle in. Let the lights go low, let your shoulders drop away from your ears, and let your breathing slow to the pace of someone who has nowhere to be and nothing left to do tonight. Wherever you are, whatever kind of day is finally letting go of you, you have arrived at the quiet end of it. There is no hurry here. There is nothing to solve, nothing to remember, nothing to hold on to. Tonight we are going to travel somewhere very far away, and the strange thing, the lovely thing, is that we will not go up into the stars to find it. We will go down, straight down, beneath the floor under you, beneath the foundations of the building, beneath the soil and the bedrock and the roots of the mountains, down into a place that no human eye has ever seen and no human hand will ever touch. And down there, resting in the dark, are two continents, not the continents you know, not the shapes you traced with a fingertip on a school map, the familiar coastlines, the countries coloured in soft pastels. Those continents, the ones we live on, the ones we name and fight over and cross in aeroplanes, are only a thin skin on the outside of the world. Tonight I want to tell you about two other continents. Continents you have never seen. Continents no one has ever seen. Continents you will never stand on, never fly over, never visit, not because they are forbidden, but because they lie 1,800 miles beneath your feet, in a place so deep and so hot and so pressed by the weight of the whole planet above it that we can only know it the way you might know a room in a house you can never enter, by pressing your ear to the wall and listening to the sounds that come through. 1,800 miles. Let that number just sit with you for a moment, the way a warm stone sits in your palm. If you could dig a tunnel straight down, and if that tunnel could somehow survive the crushing and the heat, you would have to travel about 2,900 kilometers, roughly 1,800 miles, before you reached them. That is farther than most people will ever drive in a single journey. It is the distance across an entire continent up here on the surface. And that is not the distance to the far edge of these hidden things. That is only the distance to their roof. That is where they begin. They rest at a place that geologists call the core-mantle boundary. And that name, plain as it is, describes one of the most dramatic frontiers anywhere inside the Earth. Picture the planet in layers, like the layers of something you might slice open in a warm kitchen. On the outside, the thin, cool crust, the ground we walk on. Beneath that, the mantle, an enormous thickness of hot solid rock, almost the whole bulk of the world, reaching down for thousands of kilometers. And then, at the very bottom of the mantle, that rock ends. It simply stops. And beneath it begins something entirely different, an ocean of liquid metal, molten iron and nickel, swirling and churning, hot enough that its temperature is measured not in the numbers we use for ovens, but in the numbers we use for the surface of the sun. That frontier, where the solid rock rests upon the liquid metal, is the core-mantle boundary. It is the largest change in density anywhere in the planet, a bigger jump than the one you cross every time you lift your hand up out of a bath into the open air. And it is on the roof of that molten sea, balanced on the boundary between rock and liquid fire, that our two hidden continents lie. One of them sits beneath Africa. The whole of the African continent, all its deserts and rivers and cities and coastlines, is riding, without knowing it, on the roof of one of these enormous buried structures, far below. The other sits beneath the Pacific, beneath that vast blue expanse of ocean that covers nearly half the world, beneath the waves and the ships and the deep, dark trenches. Down at the very bottom, where the mantle meets the core. Two of them. one under Africa, one under the Pacific. Almost, though not exactly, on opposite sides of the globe from each other, as if the planet had set them there on purpose, two great weights balanced against one another in the dark. And they are vast. This is the part that is difficult to hold in the mind, and I would like you not to strain to hold it, but simply to let it wash over you, the way the size of the ocean washes over you when you stand at the edge of it. Each of these structures is the size of a continent measured across, spreading for thousands of kilometers from one side to the other. But they are not flat. They are not thin smears painted onto the bottom of the world. They are tall. They rise up off the roof of the core like plateaus, like mountain ranges stacked on mountain ranges, reaching upward for hundreds of kilometers. The estimates run to something like 800, even 1,000 kilometers of height, which is roughly 500 to 600 miles. Taller than the sky is deep. Taller, many times over, than the entire thickness of the atmosphere you have breathed your whole life. If one of these things were somehow lifted up and set on the surface, it would not sit politely inside the borders of a country. It would dwarf the continent above it. The real largest continent on Earth, the biggest single structure inside the whole planet, is not any of the ones we have named. It is one of these two, down in the dark, that no one has ever seen. And together, the two of them, taking up their space at the bottom of the mantle, add up to something on the order of 6 to 9% of the entire volume of the mantle. Some careful studies push that number even higher. Think about that for a breath. Nearly 1/10 of all the vast rocky bulk of the world, that thick shell of hot rock that makes up almost the entire body of the planet, is these two piles. They are among the largest distinct things inside the Earth, and until quite recently, no one knew they were there at all. Now they have a proper scientific name, and I will give it to you softly, because it is one of those long official phrases that sounds forbidding at first, and then becomes almost comforting once you understand what it means. Scientists call them Large Low-Shear-Velocity Provinces. Large Low-Shear-Velocity Provinces. It is a mouthful, so people shorten it, the way we shorten everything, to a little cluster of letters, LLSVPs. And every part of that long name is really just a plain description of a fact, so let me unfold it for you slowly, one word at a time, because there is no rush. Large, because they are enormous, as we have said. Provinces, because that is simply a word for a big region, a territory, a distinct area with its own character, the way a province is a distinct part of a country. And then that middle part, low shear velocity, which sounds the most technical but is actually the heart of the whole thing, the reason we know these two continents are down there at all. Shear velocity is the speed of a certain kind of wave, a certain kind of trembling that passes through rock. And low shear velocity means, quite simply, that in these two regions that trembling slows down. Something passes through them, and it comes out the other side just a little bit later than it should. A little bit slower. And that hesitation, that faint lateness, that small hush in the middle of the deep earth, is the entire reason anyone ever suspected these things exist. We did not see them. We heard them slow the world down. Because here is the thing you may already be wondering, drifting there in the dark. If these are continents, if they are the largest structures inside the entire planet, if they are hundreds of miles tall and thousands of miles across, then why has no one ever seen them? Why are they not in every school book, drawn in bold colours, named and mapped like everything else? Why did I? Why did you? Why did almost everyone go their whole life without ever hearing that beneath the ground there are two more continents, older and larger than the ones we know? The answer is that we cannot reach them. And I mean that in a way that is almost hard to believe once you really sit with it. We have sent machines to the far planets. We have landed on the moon and photographed the rings of Saturn and flung a little probe out past the edge of the solar system into the cold between the stars. We have looked outward across billions of miles. But we have never, not once, dug our way down through even the thin outer skin of our own planet. Consider the deepest hole that human beings have ever made. It is in Russia, in a cold and remote place, and it is called the Kola Superdeep Borehole. For years and years, through the 1970s and 80s, engineers and scientists drilled downward, patiently, obsessively, farther than anyone had ever gone, trying simply to reach a little deeper into the ground beneath their feet. And they set a record that still stands. They reached a depth of about 12 kilometers, a little over 7 miles. It was an extraordinary achievement, and the hole grew so hot and the rock so strange and soft under its own heat that they finally had to stop. And here is the number that should make you smile in the dark at how small we are, and how large the world is. That deepest of all deep holes, that record no one has beaten, that triumph of drilling, did not even make it through the crust. It did not pierce the outermost skin of the planet. It got stuck, effectively, in the paint on the surface of the world. 12 kilometers down, and the crust in some places goes on for 30 or 40 kilometers before you even reach the top of the mantle. And then the mantle itself goes down for nearly 3,000 kilometers before you arrive at the roof of these hidden continents. So, the very deepest we have ever physically reached, the farthest any drill has ever touched, is not even 1/100th of the way to them. If the journey to these buried continents were the length of a long night's sleep, we have not yet stirred in the first minute of it. We are still lying there with our eyes closed at the very start. So no one has drilled to them. No one has sampled them. No one has ever held a piece of them in a gloved hand and turned it over under a light, and no one ever will, not with any tool we can imagine building. They are as far beyond our reach, in their own way, as anything in the sky. And yet we know they are there. We know roughly how big they are. We know where they sit, one under Africa, one under the Pacific. We know that something about them is different from all the rock around them. We have even given them names, and drawn them, and argued about them for years. All of it learned without ever going there. All of it heard, through the wall, in the dark. How? That is the question we will unfold together, slowly, as the night goes on. But let me plant the seed of it now, gently, so it can grow while you rest. The earth, you see, is not silent. It shivers. All the time, all around the world, the ground trembles, great earthquakes and small ones, faults slipping, plates grinding, the whole restless machinery of a living planet. And every one of those tremors sends out waves. Waves that race down and through the deep interior of the world, through the crust and the mantle and around the molten core, and come up again on the far side, where patient instruments are waiting to catch them. Thousands upon thousands of instruments spread across every continent, listening day and night to the ringing of the earth like the surface of a struck bell. And by measuring those waves, by timing exactly how long each one took to travel and noticing where each one arrived a little early or a little late, scientists have learned to build a picture of the inside of the world, the way a doctor builds a picture of the inside of a body without ever cutting it open. It is a kind of listening that becomes a kind of seeing. And when they built that picture, when they combined millions and millions of these measurements into a single great map of the Earth's insides, two enormous shapes appeared, two vast regions where the waves ran slow, one beneath Africa, one beneath the Pacific, rising off the roof of the molten core. The two hidden continents, revealed not to the eye, but to the ear. But I am getting ahead of the night. We will come to all of that, to the waves and the listening and the beautiful method of it, in good time. For now, I only want you to rest in the sheer fact of these two things. Two continents, hidden, enormous, ancient beyond ordinary imagining. Down there right now, exactly as they were 1,000 years ago and 1,000,000 years ago. Unmoved by any war or any winter up here on the surface, indifferent to every human life that has ever flickered on and off above them. They were there before there were eyes to see them. They will be there long after the last of us is gone. And tonight, for a little while, before you drift off, you get to know that they exist. And there is something more, something I want to whisper to you now, and then leave to unfold slowly across the hours, because it turns these two silent, patient continents into something far stranger and far more alive than mere lumps of buried rock. Because they do not just sit there. They are not simply dead weights on the floor of the world. There is a growing belief among the scientists who study them that these two hidden continents may be, in the most literal and dramatic sense, the source of the world's greatest fires. Not gently, not always, but at certain moments in the long, long history of the planet, moments separated by tens and hundreds of millions of years, the Earth has opened up and poured out fire on a scale that is almost impossible to picture. Not a single volcano, not a mountain smoking on the horizon. Whole regions of the planet, areas the size of countries, cracking open and flooding with molten rock for thousands upon thousands of years without pause, laying down layers of lava piled miles deep. These are the truly gigantic eruptions, the ones that dwarf anything in recorded human history, and they are so vast that geologists give them their own grand name. And twice, at least twice, in the deep past, one of these unimaginable outpourings of fire seems to have coincided almost exactly with the near ending of life itself, with mass extinctions, with the great dyings, when most of the living things on Earth vanished from the record, when the world was remade in ash and heat. And here is the quiet, astonishing thread that a growing number of researchers have been following. When they trace those catastrophes back, when they reconstruct where on the ancient globe those world-wounding eruptions first tore open, the locations do not scatter randomly across the map. They seem, again and again, to trace back to the same place, to the edges of these two buried continents, not their broad centres, but their steep sheer margins, the walls where the hidden continents rise up off the floor of the world. As if, along those edges, something is being launched upward from the deep. A column of heat rising all the way from the roof of the molten core to the surface of the world, and when it breaks through, the sky fills with fire. So hold that thought lightly as you drift. These two continents, these things no one has ever seen, may be the very steering wheels of the planet's deepest fires. They may be the reason the world burns, where it burns, and when it burns. The hand on the tiller, down in the dark. We will return to that idea again and again through the night, and each time we return to it, we will understand it a little more deeply, a little more calmly. The way you come to understand a piece of music by hearing it played more than once. But even now, even at the very start. It should give the two hidden continents a kind of weight in your imagination that a mere buried rock could never have. They are not inert. They may be architects. They may be the deep foundation on which the whole restless story of the surface is quietly, invisibly built. Let me give the two of them their names now. Softly, the way you would introduce two old and patient neighbors you have somehow lived beside your whole life without ever meeting. Because scientists, being human, could not go on forever calling them only by that long cold phrase, Large Low-Shear-Velocity Provinces. So the two continents were given nicknames. And the nicknames are gentle and human and honor the people who helped us first imagine the deep machinery of the world. The one beneath Africa is often called Tuzo. Tuzo, it is named in honor of a Canadian scientist, John Tuzo Wilson, a great pioneer who helped work out how the plates of the Earth's surface move and drift, and who helped us first understand the idea of these rising columns of deep heat in the first place. So the African continent, the hidden one, carries the name of a man who spent his life trying to understand exactly the kind of thing it turned out to be. Tuzo, there is something tender in that. I think that we named the largest hidden structure under Africa after a person, as if to keep it company. And the one beneath the Pacific is called Jason. Jason, honoring another founding figure, Jason Morgan, who also helped lay down the ideas of drifting plates and rising plumes of heat that we will lean on all through this night. Tuzo and Jason. Those are the two. I should tell you, so that we keep faith with the truth, that these names are informal, a friendly convention rather than an official christening, popularized by a scientist named Ed Garnereau and his colleagues, a way for the people who study these things to speak of them with a little warmth rather than only with a mouthful of letters. But the names have stuck, and they are lovely, and I will use them. Tuzo, under Africa. Jason, under the Pacific. Two hidden continents, now with names, resting in the dark beneath the world we know. And you may already feel a question forming softly at the edge of your drifting mind. If these two structures are so vast and so old and made perhaps of something different from all the rock around them, then where did they come from? How did they get there? Were they always there, from the very birth of the planet, older than any mountain, older than any ocean, older than the oldest stone you could ever pick up off the ground? Or did they gather slowly, over billions of years, built up grain by grain from material sinking down out of the world above? Or, and here is the strangest possibility of all, the one we will save for the deepest part of the night, did one of them, or both, come from somewhere else entirely? From another world? From a planet that no longer exists? Because there is a theory, a real one, argued seriously by real scientists, that one of these buried continents may be the remains of a lost world. A world that struck the young Earth long ago in the planet's violent infancy, and in dying gave us the moon that still lights our nights. But that is a story for later, when you are deeper in the dark and readier to receive it. For now, it is enough to know that the question of their origin is genuinely open, that the people who study these two continents do not fully agree on what they are or where they came from, and that this uncertainty is not a failure. It is part of the wonder. There are still, in this thoroughly mapped and photographed and measured world of ours, two continents beneath our feet, whose very nature is a mystery, whose origin is argued over in quiet rooms, whose story is still being written. And to understand any of it, To understand how we could possibly know so much about two things so utterly beyond our reach, we have to begin with the listening, with the waves, with the trembling of the whole earth and the patient instruments that catch it, and the way that a wave slowing down by just a few small percent, 1,800 miles beneath the ground, became the thread that led us all the way down to the largest hidden things inside the world. So let your breathing slow a little more. Let the number 1,800 miles drift somewhere loose and easy in your mind. And let us begin, gently, to listen to how we ever came to hear them at all. Think first of how strange it is that the earth beneath us feels so still. You lie there and the ground holds you, solid, unmoving, the most reliable thing there is. We say something is on solid ground, on firm foundation, to mean it is safe and certain and will not shift. And yet that solid ground is only the thinnest crust over a body that is anything but still. Beneath the stillness, the world is in slow, ceaseless motion. The great plates of the surface drift and grind against one another, a few centimeters each year, about as fast as your fingernails grow. And deeper down, through the vast thickness of the mantle, the hot rock itself flows, not like water, but slowly, over unimaginable spans of time. The way a thick cold honey will eventually settle if you leave it long enough. The way a glacier is solid ice, and yet still somehow flows downhill across the centuries. The inside of the world is moving. It has always been moving. And every so often, where the moving rock catches and slips, the whole planet shudders, and an earthquake is born. We tend to think of earthquakes only as disasters, and up here on the surface, where they can topple buildings and crack roads. Of course they are. But to the scientists who study the deep earth, every earthquake is also something else. It is a gift. It is a lamp lit for a moment in the darkness. Because when the ground slips and the shudder runs out through the world, it does not stay near the surface. It sends waves down, deep down, plunging through the crust and into the mantle, racing through thousands of kilometers of hot rock, bending around the molten core, and finally rising up again on the far side of the planet, where instruments are waiting in the quiet to catch them and write down exactly when they came. And those waves, on their long journey through the inside of the world, carry a message. They carry, written invisibly into their timing, the story of everything they passed through. Because a wave that travels through cold, dense, stiff rock moves at one speed, and a wave that travels through hotter or softer or different rock moves at another. Speed up here, slow down there. And so a wave arriving on the far side of the world, arriving a fraction of a second earlier or later than it should, is telling you something about the hidden places it crossed on the way. It is describing, in the only language it has, the rooms of the house it moved through in the dark. There are two main kinds of these waves, and it is worth knowing them by name, softly, because the very name of our hidden continents is built from one of them. The first kind is a pushing, squeezing wave that races ahead by compressing the rock in front of it and letting it spring back, the way a sound moves through the air. These are the fast ones, the ones that arrive first, and scientists call them P waves. The second kind is a shaking, sideways wave that moves by wobbling the rock from side to side as it passes, the way a shudder travels along a rope you flick at one end. These are slower, and they arrive a little later, and they are called S waves. Shear waves. That word shear, meaning that sideways, side-to-side, shaking motion. And now, perhaps, that long cold name is beginning to soften and open in your mind. Large Low-Shear-Velocity Provinces. Large regions, deep down, where the shear waves, the S waves, the sideways, shaking ones, travel low, travel slow. That is all it means. Two enormous regions at the bottom of the mantle where the shaking waves passing through are held back, slowed by just a few percent compared to how fast they run through all the ordinary rock around them. A few percent. Such a small hesitation. And yet, gathered up across millions of waves and millions of earthquakes and thousands of listening instruments all over the world, that small hesitation drew a shape that would not go away, a shape that appeared again and again, no matter who did the listening or how they did the measuring. Two great slow continents, standing on the roof of the molten core, patient and enormous and, until we learnt to listen, entirely unknown. So the question that naturally settles in next, quiet and patient as the dark itself, is this one: how do we actually know? How does a hesitation of a few percent in the speed of a wave that nobody will ever touch, travelling through rock that nobody will ever see, at a depth that no drill and no human instrument has ever reached, become a picture? How does a sound become a continent? The answer is a method that has a name, and the name is seismic tomography. Tomography, you may have heard that word before in a different setting entirely, in a hospital corridor perhaps, or in a doctor's office where someone explained that a scan was needed, a cross-sectional scan. A way of building an image of the inside of something without cutting it open. That is exactly what it means here. The word tomography comes from the Greek word for a slice, and the idea is the same whether the object being sliced is a human body or a planet. You send energy through the object from many directions. You measure how long it takes to arrive and how it changed along the way. You put all those measurements together and you assemble a picture of what is inside. A picture made of inference and mathematics rather than light, but a picture nonetheless. In a hospital, the energy is X-rays, and the machine that generates them rotates in a circle around the patient, building up its cross-sections methodically and deliberately, under controlled conditions. Seismic tomography is less orderly than that, and in some ways that disorder is what makes it work. The Earth generates its own energy, all the time, without being asked. Every earthquake that happens anywhere in the world sends waves radiating outward from its source in every direction at once, waves that travel not just along the surface, but straight down into the interior, bending and bouncing and ricocheting through the deep rock in trajectories shaped by everything they pass through. The planet is constantly ringing itself, like a bell struck over and over from different points, and those vibrations, if you know how to listen, carry the story of what is inside. And we have learned how to listen. Around the world there are thousands of seismometers, sensitive instruments fixed to the rock in dedicated stations. In basements and vaults and quiet places well away from traffic and machinery, their job simply to detect any motion in the ground, no matter how faint and no matter from how far away. When a large earthquake happens on one side of the planet, its waves arrive at seismometers on the other side minutes later, weakened but still readable, their travel time recorded to fractions of a second. The difference between the time a wave was expected to arrive, based on a model of what a perfectly uniform Earth would look like, and the time it actually arrived, is the signal. Arrive early, and the wave sped up somewhere along its path. Arrive late, and it slowed. Do that calculation for millions of waves from thousands of earthquakes recorded at thousands of stations. And the deviations from expectation pile up, redundant and overlapping, and from that pile of deviations a three-dimensional image slowly resolves. Slowly, patiently, the inside of the Earth comes into focus. The images that result are the ones you may have seen reproduced in textbooks and on the screens of science documentaries. Those striking cross-sections of the planet, coloured in the deep blue of cold, dense rock and the deep red of slow, hot rock, like a thermal scan of something enormous and alive. Blue is fast, where the waves move quickly through material that is dense and relatively cool. Red is slow, where the waves wade through something that is warm or different or both. And in those images, consistent and unmistakable across the work of different teams, using different data and different mathematical approaches. Two great patches of red resolve at the very bottom of the mantle. One beneath Africa, one beneath the Central Pacific, sitting on the core-mantle boundary like two enormous cushions, patient and immovable, glowing their quiet, slow red in every model that has ever tried to see them. The consistency matters enormously. Science is full of results that appear once and then fail to be reproduced, features that look real in one dataset and dissolve in another. The two provinces are not like that. They show up in every serious global tomographic model. Different teams with different philosophical approaches to how they process the data. Different choices about which earthquakes to include and how to correct for the effects of the crust, different numerical methods for inverting the travel times into a velocity structure, and yet the answer keeps coming back the same. Two large, slow, deep structures, approximately where we thought they were, approximately the shape and size the models agree on. A discrepancy from the expected speed of the same order of magnitude in every version. That convergence, that independent agreement, is what allows geophysicists to say, with confidence, these things are real. Whatever they are there. Now you might wonder, and it is a reasonable thing to wonder, why the shear waves in particular are the ones that carry most of the story. Why do the S-waves, the sideways shaking ones, the ones that give the provinces their name, matter more than the P-waves, the pushing compressive ones? The answer has to do with what each type of wave is sensitive to, and this distinction is at the heart of one of the most important arguments in all of deep Earth science. Both wave types slow down when they enter hot material. Heat loosens rock, makes it less stiff, makes it harder for a wave to push through cleanly. So both a P wave and an S wave arriving late, both slowing down compared to expectation, could simply be telling you that the region they pass through is warmer than average, and for a long time, a warm region is exactly what many scientists assumed they were seeing in the deep mantle. Hot blobs. Upwellings, material that had absorbed more heat from the core and was therefore a little slower, a little softer, a little more sluggish when a wave tried to pass through it. But the two wave types are not equally sensitive to everything. The shear wave, the S wave, is particularly responsive to the rigidity of the material it passes through, to how well the rock resists being twisted and sheared sideways. The compressive wave, the P wave, is sensitive to both rigidity and to bulk modulus, which is the material's resistance to being compressed, squeezed inward. And crucially, when you change the chemistry of a rock, when you change what it is actually made of, rather than simply how hot it is, the two wave types respond differently. A change in temperature tends to slow both waves, but in a predictable ratio. A change in composition, a change in the actual minerals making up the rock, changes the two wave types in ways that deviate from that thermal ratio. There is a third quantity that researchers can derive by combining P-wave and S-wave speeds, and it is called bulk sound velocity. It is a way of isolating, mathematically, the part of the wave behavior that comes purely from the compressibility of the material, the squeezing part, separated from the rigidity part. And when seismologists compute the bulk sound velocity inside the two provinces, something unexpected happens. Where the S waves are slow, as you would expect from a warm region, the bulk sound velocity behaves differently from what a simple heating explanation would predict. In the large, slow provinces, the bulk sound velocity and the S-wave velocity move in opposite directions, in a way that is very hard to explain by temperature alone, but fits reasonably well if the material itself is chemically different, made of different stuff, denser stuff. Stuff that is not the same as the ordinary rock that makes up the rest of the surrounding mantle. This is not a small detail. It is one of the central arguments for what these provinces really are. Not merely warm patches of ordinary mantle that absorbed more heat from the core, something compositionally distinct. A different kind of rock sitting in the same place, for reasons that are still being argued. And the argument deepens when you look not at the interior of the provinces, but at their edges. If you had two enormous blobs of warm material sitting at the base of the mantle, warm and therefore less dense, and therefore buoyant, you might expect their outlines to be gradual, diffuse, their boundaries blurring gently into the surrounding rock, the way a drop of warm water blurs into a cold glass. Heat spreads. Diffusion rounds edges. A purely thermal feature tends to have soft margins, a gradual shading from warm to less warm to ordinary, a feathering at the boundary rather than a hard line. The provinces do not have soft margins. The African province in particular, where the seismic coverage is richest and the models are most detailed, shows edges that are steep, sharp, near vertical walls of anomalous material that rise from the core-mantle boundary and maintain a dramatic abrupt change from slow to fast across a boundary that in some places appears to be astonishingly narrow, perhaps only a few tens of kilometers across, in a structure that is hundreds of kilometers tall and thousands of kilometers wide. Not a gradual thermal smear. A wall. Think of it this way. Imagine you have a large aquarium filled with water, and you add a blob of cooking oil to one corner. The oil, being less dense than the water, floats. Over time, the surface tension keeps it loosely together, but its edges drift and blur, and the oil slowly disperses. That is roughly how a purely thermal blob would behave in the mantle over hundreds of millions of years. Now imagine instead that you drop a blob of dense honey into the same aquarium. The honey sinks because it is denser than the water, and when it reaches the bottom, it pools there, spreading perhaps but maintaining a relatively coherent shape, holding together because its density keeps it from floating away, its cohesion keeping its edges intact. The sharp margins of the provinces argue for something much more like the honey than the oil. Something that holds together not in spite of gravity but because of it. This is the model that many geophysicists find most compelling when they look at the combined evidence, and it has a name, the thermochemical pile hypothesis. Thermo, meaning heat, because the provinces are certainly warm, sitting as they do on the boundary with the molten core and having absorbed billions of years of heat from below. Chemical, because their composition appears to be genuinely different from the surrounding mantle. Pile, because the model envisions them as heaps, accumulations, dense deposits that have settled by gravity to the lowest available floor and remained there, stable and persistent, because their excess density pins them in place. The density difference involved is not dramatic on the scale of everyday experience. Published estimates suggest the LLSVP material may be on the order of a couple of % denser than the ambient mantle around it. 2%. In human terms, that sounds trivial. If you are carrying a bag that weighs exactly 100 pounds, 2% heavier means 2 extra pounds, barely noticeable. But in the mantle, over geological timescales, 2% is enormous. The mantle is not water or air, it is solid rock, and in solid rock even tiny density differences, accumulated over millions and billions of years, produce powerful and irreversible consequences. A material 2% denser than its surroundings, sitting at the bottom of a mantle 3,000 kilometers deep, is not going to float. It is not going to get mixed up by convection the way lighter material does. It is going to sit there, heavy and patient, pooled at the lowest available point, and it is going to stay. The physics of why such a pile would maintain steep sides rather than slowly spreading flat like pancake batter on a griddle is a matter of ongoing research, but the intuition is this: the pile is denser than the surrounding mantle, so it sinks toward the boundary. But it is also warmer than the surrounding mantle, because it has been sitting against the hot core for so long, and warm material is buoyant, which pushes it upward. These two competing forces, the pull of density downward and the push of heat upward, reach a kind of dynamic truce at the edges of the pile, a balance point where the material is neither rising nor sinking, but simply holding, maintaining those steep walls like a sandcastle holds its shape at the beach, not because it is rigid, but because the angle of the slope is exactly the angle at which the competing forces balance. The thermochemical pile lives at the bottom of the mantle in something like that equilibrium, dense enough to stay, warm enough not to collapse entirely, its edges maintained by the tension between those two forces over hundreds of millions of years. There is a further detail worth sitting with, a smaller structure that lives at and around these edges. A structure that takes the strangeness of the provinces and raises it by another order of magnitude. They are called ultra-low velocity zones. The name is a signal of how extreme they are, so extreme that they needed the word ultra added to the front of a description that was already describing something slow. These are patches, scattered across the margins of the two great provinces, that are not merely a few % slow, but dramatically, shockingly, tens of % slow. Shear wave velocities dropping by amounts that in some cases approach a third of their normal value. Where the provinces themselves are a whisper, the ultra-low velocity zones are a shout. They are small by the standards of the deep earth, a few to a few tens of kilometers thick, perhaps tens of kilometers across in some cases, whereas the provinces themselves span thousands. But they are real, they are repeatable in independent studies, and they tend to cluster at the margins of the large, slow provinces, gathered at the edges rather than distributed across the interior. As if whatever makes them extreme is somehow concentrated at the boundaries of the bigger structures. What are they? This question is even less settled than the question of what the provinces themselves are. Two leading ideas compete. One is that the ultra-low velocity zones contain iron-rich material, rock with an unusually high concentration of iron compared to ordinary mantle, which would make it especially dense and give it unusual wave properties. The other, and perhaps more evocative, possibility is that these zones are partially molten, that within them, scattered in tiny pockets or pooled in larger reservoirs, there is actual liquid rock, melt, sitting right at the base of the mantle against the interface with the molten iron core. If that is true, They would be the deepest reservoirs of liquid rock inside the Earth. Melt pockets resting on the roof of the outer core, nearly 3,000 kilometers down. In conditions of pressure and temperature so extreme that the rock there behaves in ways that have no analogue anywhere on the surface. Some things here at the top of the world have names and categories that fit them comfortably. The ultra-low velocity zones resist that kind of comfort. They are anomalies atop anomalies, mysteries nested inside mysteries, sitting at one of the most dramatic frontiers the planet possesses. And that frontier, the place where the provinces sit and where these extreme zones cluster, deserves its own moment of attention. Because the floor on which these structures rest is not merely the bottom of the mantle. It is something quite specific and quite extraordinary, and geophysicists have a name for it that is worth knowing: the core-mantle boundary. The core-mantle boundary, at a depth of approximately 2,900 kilometers, roughly 1,800 miles beneath your feet, is one of the most dramatic physical interfaces anywhere inside the planet. More dramatic, in fact, than the surface of the Earth itself, at least in terms of the density contrast it represents. When you stand on a beach and look out at the ocean, there is a boundary between air and water, and that boundary is real and obvious, the densities of the two materials differing by a factor of about 800. When you look at the ground beneath your feet, there is rock and then there is air, and that contrast is even greater. But the core-mantle boundary is something else entirely. On one side of it, the solid silicate rock of the lower mantle, heavy and dark and compressed into minerals that only exist under that unimaginable weight. On the other side, the outer core, liquid iron and nickel, a metallic ocean that is not water and not rock, but something in between. Metal in its liquid state, churning and flowing under conditions of pressure and temperature that no material at the surface has ever experienced, and no laboratory has fully reproduced. The density contrast between solid silicate rock and liquid iron is enormous, not the same as the contrast between rock and air, but comparable in order of magnitude. This boundary is, in the language of geophysics, the largest density discontinuity anywhere inside the Earth. A more abrupt, more fundamental transition than any mountain range or ocean trench, than any junction between crust and mantle, or between the lithosphere and the asthenosphere. The most dramatic line inside the planet is the one you cannot see and will never approach. The one that sits at the bottom of a column of rock nearly 2,000 miles deep. The temperature at this boundary is genuinely difficult to hold in your mind. Published estimates for the temperature of the core-mantle boundary range in the neighborhood of 3,700 to 4,000 degrees Celsius, roughly 7,000 degrees Fahrenheit, a temperature comparable to the surface of the Sun. Not the interior of the Sun, which is incomparably hotter, but the photosphere, the visible surface, the layer from which sunlight actually escapes. The rock of the lower mantle, sitting directly above this boundary, is absorbing heat from something that is as hot as a star's outer edge. That heat is not an abstraction. It is a physical reality that has been flowing for 4.5 billion years, from the cooling core outward through the mantle and eventually to the surface, driving the geological engine of the planet, warming the rock above the boundary, and setting in motion the slow convection currents that carry continents on their patient, incomprehensible journeys. The provinces, Tuzo and Jason, sit directly on this boundary. They are in contact with it. Their bases are pressed against the interface between solid rock and liquid metal. between the mantle and the outer core, absorbing heat from the hottest accessible region inside the planet. They are not close to this boundary, or near it, or a few hundred kilometers above it. They are on it, resting with their feet in one of the most extreme environments the Earth possesses. And that boundary has a second layer worth naming. The lowermost few hundred kilometers of the mantle, the zone directly above the core-mantle boundary, where the provinces live and where the ultra-low-velocity zones scatter themselves, has its own name in the technical literature. It is called D double prime, written with the letter D and then two small quotation marks, D. A notation that arrived in the literature decades ago and has simply stayed one of those pieces of scientific jargon that outlasted its original justification and became the accepted term for a layer that is, by any measure, one of the strangest places inside the planet. If you ever meet that term, D double prime, know that it means this deepest mantle basement, this lowermost rind of solid rock sitting above the liquid iron, the floor on which the provinces stand, and the ceiling through which the core's enormous heat must pass on its way upward. The D double prime layer is not a uniform slab. It is complicated, varied, structured in ways that only decades of improving seismic tomography have begun to reveal. It contains the provinces themselves, those vast, slow continents. It contains the ultra-low velocity zones scattered at their margins. It contains regions of fast, dense material where ancient slabs of cold oceanic rock, subducted at the surface perhaps 100 million years ago, have finally sunk all the way to the bottom and pooled there in their own graveyard. And threading through all of this, there is the transition, the crossing from the solid silicate of the mantle into the liquid iron of the core. A transition that is itself not perfectly sharp, but has its own internal structure, its own gradients and anomalies, its own seismic character. D double prime is less a single thing than a populated landscape, a deep basement with its own geography, its own residents, its own weather, if you will, expressed not in cloud and wind, but in heat flow and density and chemical gradient. In 2004, a discovery added a new resident to this landscape. Researchers identified a new high-pressure mineral, a form of mantle rock that exists only under the extreme conditions of the lowermost mantle, the conditions of D double prime. It is called post-perovskite. The name tells you something about what preceded it, ordinary deep mantle rock, under the pressures above D double prime, takes a crystalline form called perovskite. And post-perovskite is simply what that mineral transforms into when squeezed and heated to the even more extreme conditions near the core-mantle boundary. The structure of its crystals is different, its seismic properties are different, and its existence helped explain several previously puzzling seismic features of the lowermost mantle. Post-perovskite is a reminder that at these depths, rock is not simply rock in the way we mean on the surface. The category of mineral, the actual atomic arrangement inside a crystal, changes with depth and pressure in ways that have no everyday parallel. What the provinces are made of is not merely a question of what elements are present, but of what phase, what crystalline form, the pressure and temperature at the core-mantle boundary will allow. And so the slow signal in the seismic waves is carrying not one story, but several layered on top of each other. A wave slowing down as it passes through the lower mantle near the African or Pacific province is telling you, simultaneously, something about the temperature, something about the composition, something about the mineral phase, something about the possible presence of partial melt. Unbraiding those signals, assigning to each percentage of slowdown its correct cause, is the ongoing work of geophysics, and it is not complete. The picture is clear enough to see the shape. It is not yet clear enough to read every detail. What is settled is this: the provinces are real. They are large. They have been detected independently by many different researchers in many different models. They have steep edges. Their wave properties argue for a composition distinct from ordinary mantle rock, and they have been sitting at the base of the mantle for a very long time. The existence is beyond reasonable scientific dispute. What they are made of, where that material came from, and exactly how it behaves, those questions are alive and contested and being worked on right now in universities and research institutes on several continents by people who have devoted their professional lives to listening to the planet breathe. Take a moment, if you will, to let the sheer fact of this settle. The most powerful geological tools humanity possesses, the algorithms and the seismometer networks and the supercomputers that invert millions of travel time measurements into three-dimensional maps, have been aimed at the inside of this planet for decades. And what they have found, patient at the bottom of all that rock, are two structures so large that the word continent is not an exaggeration or a metaphor, but a genuine descriptor, a proportionate statement of size. Each one spanning thousands of kilometers across. Each one rising hundreds of kilometers above the floor it rests on, together making up several percent of the total volume of the mantle. A volume already so large that the human mind cannot honestly compass it. And nobody put them there. They were not built, they are not manufactured or designed. They assembled over billions of years through processes that are still being reconstructed, and they persist through physical forces that keep them from dispersing, dense enough to pool, warm enough not to collapse, held at the bottom of everything by the same gravity that holds you in your chair. They are a natural consequence of the planet's own history, its thermal evolution, its tectonic history, the accumulation of 4.5 billion years of geological process arriving at the present moment as two great silent presences, far below the ground, you know. There is something worth dwelling on in the fact that we found them by listening, not by drilling, not by sending instruments down, not by any direct approach, but by learning to read the hesitations in the signals passing through. The earth rang itself, as it has been ringing itself for as long as there have been earthquakes, and for most of human history those rings were either unfelt or felt only as disaster, as destruction. It was only when we built instruments sensitive enough to hear the faint echoes and mathematical methods sophisticated enough to reverse engineer their travel histories that the ringing became information, that the hesitation of a few percent in a sideways wave, 1,800 miles down, resolved into a shape with edges, a shape with a floor and a ceiling, a shape large enough to call a continent. The images that come from this process, those cross-sections of the deep earth coloured in slow red and fast blue, are among the stranger and more beautiful things human science has produced. They look almost organic, like scans of a living body, which in a geological sense is exactly what they are. The hot red of the provinces glows in them against the cooler surrounding material, and if you look at a global map of the D'' layer, you see them both, the African one spreading beneath the continent above it and stretching out under the southern Atlantic, and the Pacific one beneath the central ocean that shares its name, each one enormous, each one anchored to the core-mantle boundary, each one radiating slow red in every model that has tried to see it. Two slow continents, two buried worlds, resting in a layer of the earth that has its own strange name and its own strange inhabitants, above an ocean of liquid iron as hot as the surface of the sun. And this is where the next question lives, the question that the structure of the provinces makes almost inevitable once you have understood what they are and where they sit. If these great dense piles are pressing against the hottest boundary in the planet, absorbing enormous amounts of heat from the molten core below, that heat has to go somewhere. It cannot simply accumulate. And the shape of the pile, the chemistry of the pile, the density and the geometry and the steep walls that hold the edges in their dynamic truce, all of those physical details matter enormously for what happens to the heat and where it goes. The provinces are not simply sitting there passively. They are doing something to the heat. They are organizing it, channeling it. And the question of where the heat goes and how the steep edges of these structures focus and direct the energy rising from the core is the question that connects these two buried continents to the volcanoes above, to the islands and the rifts and the great scarring outpourings that have shaped the surface world and, twice in particular, nearly ended the story of life upon it. But that mechanism, that steering, that channeling of fire through the deep architecture of the planet asks for its own unhurried telling. The thermochemical piles have been introduced. The floor they rest on has been named and described and given the temperature it deserves. The method by which we found them has been laid out, from the first earthquake wave to the last blue and red image. What remains is to follow the heat as it rises from the core and meets the edges of those steep walls, to trace the path from two buried continents to the surface of the earth. To ask why the margins specifically, not the broad slow interiors, but the narrow steep borders, are the places where the planet has chosen, again and again, across hundreds of millions of years, to erupt. Think of the way water behaves when it meets a steep rock wall in a river. Flowing along the flat riverbed, the water moves evenly, spreading its energy across the width and the depth, distributing itself without urgency or direction. But where the bed rises, where a wall cuts the channel and forces the flow to angle and compress, something changes. The energy that was diffuse becomes concentrated. The current that was broad becomes narrow and focused and fast. The wall does not create the energy, it simply tells the energy where to go. It organizes what was formless, it gives direction to what had none. The steep edges of the two great provinces work on heat in something like that way. Not because heat is a river, and not because the analogy holds at every level of precision, but because the essential logic is the same. The core-mantle boundary is releasing enormous quantities of heat upward, steadily and without pause, and that heat rises into the lowermost mantle and spreads out beneath the great rocky ceiling of the D-double-prime layer. Where it meets open, relatively uniform mantle material, it diffuses. It rises gently, broadly, without a preferred path. But where it meets the steep side of a thermochemical pile, the geometry changes. The wall is hotter than the surrounding mantle, heated from below and insulated by the dense, chemically different material of the province itself. And that hot wall, rising hundreds of kilometers from the floor to the interior of the mantle, is not a static surface. It is a thermal boundary, and thermal boundaries in the deep earth are profoundly, fundamentally unstable. The physics of this instability is not exotic. It is the same physics that makes hot air rise above a candle flame and cold air descend near a winter window. When rock at the base of the mantle is hot enough, dense enough with heat but not dense enough with mass to stay where it is, it becomes buoyant, It wants to rise. And the question that has occupied researchers for decades is exactly where, along the enormous three-dimensional surface of the two provinces, that buoyancy organizes itself into a coherent, upward motion rather than simply diffusing away. The answer, which has become clearer and more consistent across multiple independent lines of seismic and geodynamic study, is that it organizes at the edges. Not at the broad, slow interiors of Tuzo and Jason, not somewhere in the middle of the African province, where the pile is thickest and warmest and most thoroughly chemically isolated from the surrounding mantle. The edges. The steep, near-vertical walls, those sharp margins that seismic imaging has revealed to be surprisingly abrupt, almost cliff-like in their geometry. It is there, along those margins, that the thermal boundary layer between the base of the mantle and the overlying rock becomes most violently, most productively unstable. The heat from the core, flowing upward and outward, reaches the sloping side of the dense pile and is, in a sense, funneled, concentrated, forced to rise not broadly but narrowly, gathering in the zones where the geometry of the pile focuses it most. And from those zones, plumes are born. A mantle plume is a column of rock, always solid, never liquid, always moving, always barely moving by human standards, that has become buoyant enough to rise slowly through the surrounding mantle over millions and tens of millions of years. It is not a jet of magma shooting upward. It is nothing so violent or fast. It is a column of warm, solid rock, perhaps 100 kilometers across at its base, rising at a pace measured in centimeters per year, carrying heat from the deepest mantle toward the base of the lithosphere, the rigid outer shell of the planet. The column is driven by its own buoyancy. The rock around it is slightly denser, slightly cooler, slightly less willing to move. And so the plume rises through it the way a bubble rises through honey, slowly, persistently, over geological time, maintaining its column-like form while the world above it continues to shift and change. When that column of buoyant rock reaches the base of the lithosphere, it spreads out. It cannot penetrate the rigid plate above it in any ordinary way, so it flattens and flows outward, heating the plate from below. And where the plate is thin enough, or where the plume is hot enough and the pressure from below is sufficient, that heat reaches the surface. It decompresses as it rises, which drives melting, and the melt finds its way upward through the lithosphere and erupts as volcanic activity. What you see at the surface, the volcano, the island chain, the lava fields, is the terminal expression of something that began not in the crust, not in the shallow mantle, but in the lowest few hundred kilometers of the planet. Close to the core-mantle boundary, close to the steep edges of one of the two great buried provinces. The term researchers use for these edge zones, for the specific regions along the margins of the two large low-shear-velocity provinces from which plumes appear to preferentially rise, is plume generation zones. The name is straightforward, almost modest, for something so consequential. But the modesty is appropriate. These are not precise, surgically defined lines on a map of the deep earth. They are statistical associations derived from the painstaking work of reconstructing where the planet's volcanic hotspots have been over hundreds of millions of years, and then comparing those reconstructed positions against seismic images of the province's edges. The association is strong enough that most researchers in this field treat it as real. The margins of Tuzo and Jason are where the planet preferentially chooses to launch its deep fire. At the surface, this shows up most clearly in the world's great volcanic hotspots, Those places where a long-lived source of deep heat has been punching up through a moving tectonic plate for millions of years, leaving a trail of volcanic islands or lava fields that record the plate's motion like a register of punched holes. Hawaii is the most famous example, and it sits above the Pacific province, above Jason. The chain of Hawaiian islands, stretching northwest from the youngest volcanoes on the Big Island toward the progressively older, progressively more eroded peaks of the northwest chain and then the seamounts and atolls of the Emperor chain, is a time-lapse recording of the Pacific Plate moving over a relatively fixed deep source. That source, the Hawaiian plume, is one of the best-studied mantle plumes on Earth, and its deep route, where the seismic evidence can be followed downward with any confidence, reaches toward the edges of the Pacific Large Low-Shear-Velocity Province. Toward Jason. Across the planet, above Tuzo, the picture is different in geography but consistent in principle. Iceland sits on the mid-Atlantic ridge, the volcanic spreading center that runs roughly the length of the Atlantic Ocean from north to south. Most of the ridge is submarine, producing ocean floor that spreads slowly in both directions, creating new seafloor one increment at a time. But Iceland rises above sea level, a volcanic island of extraordinary activity, because something extra is feeding it from below. That something is the Iceland plume, a deep source of buoyant hot material that has been pushing up beneath the North Atlantic for tens of millions of years, and whose deep root traces in seismic tomographic models. Toward the margins of the African Large Low-Shear-Velocity Province, toward Tuzo. Further south, the island of Reunion, small and steep and volcanically active in the Indian Ocean, is another candidate, another surface expression of a deep plume that statistical studies associate with the African province. And the East African Rift System, that great cracking of the African continent that runs from Mozambique northward through Tanzania, Kenya, Ethiopia, and into the Afar region, where three tectonic plates are slowly, painfully pulling apart, has long been associated with an upwelling of hot material from below. The Afar hotspot and the broader East African rifting are among the most dramatic ongoing examples of a plate being stretched and thinned from beneath, and the deep source of that heat, as best as current seismic studies can determine, connects downward toward Tuzo. Some lists of candidate plume generation zones also include Yellowstone, that great geothermal field beneath Wyoming where the ground breathes steam and the geysers keep their ancient schedules. But Yellowstone is worth flagging as a more complicated case. The origin of the Yellowstone hotspot, and whether it truly represents a deep mantle plume rooted near the core-mantle boundary or a shallower, more lithospheric phenomenon, is debated among researchers. The association with a large low-shear-velocity province is not as clear or as well established as it is for Hawaii or Iceland. So Yellowstone can be named as a candidate, as a surface feature that may carry the fingerprint of the deep provinces, but with the honest acknowledgement that its deep story is not as settled as the stories of Hawaii or Iceland or Reunion. What is clear, and what is the sharper, stranger, more important half of what the title of this documentary promises, is not simply that the provinces give rise to plumes that feed volcanic islands. Volcanic islands are wonderful and dramatic and the subject of their own long story, but they are not what the dossier means by the planet's deepest fires. The deepest fires, the most consequential eruptions in the history of the Earth, are the large igneous provinces, the LIPs. A term that is almost comically understated for what it describes. A large igneous province is not an island chain. It is not a single volcano. It is a planetary scar, a flood of lava so vast and so sustained that it changes the chemistry of the atmosphere, the temperature of the oceans, and the course of life on the surface for millions of years. It is what happens not when a plume feeds a hotspot, but when a plume, or something very like one, erupts not through thin oceanic crust, but through thick continental crust, or on an extraordinary scale, and the result is not a mountain, but a province, a terrain, a new geography made entirely of solidified basalt, sometimes kilometers thick and thousands of kilometers wide. There have been dozens of large igneous provinces in Earth's history, but two of them carry particular weight, particular darkness, in any accounting of what these deep structures have done to the surface world. The first is the Siberian Traps. About 252 million years ago, in what geologists call the End Permian, a vast volcanic outpouring began in what is now the region of Siberia. The eruptions went on for what, in human terms, is unimaginable, hundreds of thousands of years, perhaps longer, pouring out basalt over an area estimated in the millions of square kilometers. The gases released, the sulfur dioxide and the carbon dioxide, the halogens and the particulates, disrupted the climate and acidified the oceans and stripped the ozone layer with a ferocity that life on Earth had not previously encountered in its long history. The End Permian extinction is the largest mass extinction in the fossil record. Somewhere between 70 and 90% of all marine species and roughly 70% of vertebrate species on land did not survive. The world after the Siberian Traps was a different world, populated by different survivors, running on different ecological rules. Everything that came after, including eventually the mammals, including eventually the line that became human beings, came after because the Siberian Traps reorganized the hierarchy of life on Earth. The reconstructed position of the Siberian Traps, traced back to where the eruption would have been located relative to the tectonic plates at the time it occurred, some 252 million years ago, aligns statistically with the margins of the Large Low-Shear-Velocity Provinces. The edges. The plume generation zones. The suggestion, supported by multiple studies, is that the deep source that fed the Siberian Traps, the mantle plume or plume cluster that drove that catastrophic outpouring, originated at the edge of one of the two buried continents resting at the core-mantle boundary. The second of these great marking events is the Deccan Traps. About 66 million years ago, in what geologists call the Cretaceous-Paleogene boundary, another vast volcanic outpouring began, this time centered in what is now the Deccan Plateau of western India. The Deccan eruptions were also enormous by any measure, producing hundreds of thousands of cubic kilometers of basalt over a period that overlaps with, and may have interacted with, one of the most famous single events in Earth's history. 66 million years ago, an asteroid roughly 10 kilometers across struck what is now the Yucatan Peninsula of Mexico. The impact and the chain of consequences it triggered, the firestorms and the atmospheric winter and the collapse of food webs, ended the age of the non-avian dinosaurs, the most spectacular and long-lived group of large animals the world had yet produced. The Deccan eruptions were already underway when the asteroid struck, and they continued after. The relative contributions of the volcanism and the impact to the extinction remain a subject of genuine scientific argument. But the Deccan traps are real, and their reconstructed deep source, traced back through the plate movements of the past 66 million years, aligns again with the margins of the Large Low-Shear-Velocity Provinces. With the edges of Tuzo, another catastrophe, another mass extinction, another chapter of radical reorganization in the history of life, bookmarked by an eruption whose deep roots appear to reach down to the sloping sides of one of the two buried continents. The word that the outline uses for this, timers, is an evocative one, and it carries more weight on reflection than it might seem to at first. The provinces do not cause these eruptions the way a trigger causes a gun to fire in a simple, immediate, mechanical sequence. The timescales are too slow, the processes too complex, the contributions of other factors too real for that kind of determinism. But the statistical association between the edges of the Large Low-Shear Velocity Provinces and the sites of the world's most consequential volcanic events is consistent enough across enough independent studies to suggest that the provinces are part of the causal story, that the geography of the deep Earth, the locations of those steep thermal walls 2,900 kilometers down, has shaped which regions of the surface have been visited by catastrophic heat over hundreds of millions of years. That beneath the familiar map of plates and continents and ocean basins lies a deeper map, a more permanent map, whose edges mark where the planet has chosen, again and again, to erupt. This is what the title means by steering. Not a metaphor, a mechanism. It is at this point in the telling of these two buried continents that it becomes appropriate to stop and give them their names. Because names, even informal ones, do something that coordinates and designations cannot. They make the abstract specific. They tie a vast, invisible, barely comprehensible structure to a human being who spent their life trying to understand it. The African province, the one beneath the continent whose name it shares and whose margins may have launched the plumes that fed the Deccan traps, is called Tuzo. The Pacific province, the one beneath the ocean, the one whose edges reach toward Hawaii, is called Jason. These are nicknames, informal labels that circulate in the scientific and popular literature rather than in official nomenclature. No governing body of geophysics has formally decreed these names. They are a form of tribute, a way of honoring two figures who laid foundational work in understanding the deep Earth and the motion of its plates. Tuzo honors John Tuzo Wilson, a Canadian geophysicist who worked through the middle decades of the 20th century and contributed in essential ways to the development of plate tectonic theory. Wilson was among the first to articulate the concept of hotspots, those long-lived, relatively fixed deep sources that leave trails of volcanic islands as plates move over them, and the concept of mantle plumes as the mechanism carrying heat from the deep Earth to the surface. The African province, that great thermal structure whose edges appear to generate the plumes that feed the hotspots Wilson helped us understand, carries his name. It is a quiet honor, the kind that scientific communities sometimes offer, naming something enormous and invisible after someone who spent their life arguing it must exist. Jason honors Jason Morgan, another founding figure of plate tectonic theory, who in the early 1970s formalized the theory of mantle plumes with mathematical rigor and proposed that fixed, deep sources, rising columns of hot material from the base of the mantle, could explain the pattern of hotspots observed at the surface. The Pacific province, whose edges seem to be the launch point for the Hawaiian plume and for other deep sources, carries his name. The names themselves were popularized notably by the geophysicist Edgar Nero and colleagues. who brought them into wider circulation as the seismic evidence for the two provinces became clearer and more detailed. It is worth saying again that Tuzo and Jason are informal names, that the structures they refer to are formally the Large Low-Shear-Velocity Provinces, but that the informal names have a warmth and a specificity that the formal designation lacks, and that they carry a real meaning, a reminder that the invisible architecture of the deep earth was found by people, by specific people with specific ideas who argued and measured and revised their thinking over decades. Now consider what sits at the edges of these provinces, at the places where the plumes are born, more closely. Because the Large Low-Shear-Velocity Provinces are not the only anomalous structures at the core-mantle boundary. Sitting on top of them and clustering specifically around their margins are features even smaller and even more extreme, zones of seismic strangeness that the measurements render in their own technical language. These are the ultra-low velocity zones. The name is not poetry, it is description. If the Large Low-Shear-Velocity Provinces are regions where seismic waves slow by a few percent compared to the surrounding mantle, the ultra-low velocity zones are regions where they slow by tens of percent, not 2 or 3%, tens of percent. A shear wave that passes through one of these zones is arriving measurably, dramatically late compared to a wave travelling the same distance through ordinary deep mantle rock. The difference is not a calibration question or a model artifact. It is one of the sharpest seismic signals the deep earth produces. The ultra-low velocity zones are small by comparison to the large provinces. They are typically described as tens of kilometers across in their horizontal extent, and a few tens of kilometers thick, sitting right at the core-mantle boundary. In a planet with a radius of about 6,300 kilometers, they are tiny. In human terms, some of them are not much bigger than a medium-sized city in horizontal extent. But what they represent, in terms of the physical state of the rock or whatever material that occupies them, is something far more extreme than the provinces above them. Seismic waves slow that dramatically for a limited number of physical reasons. The material could be much hotter than the surroundings. It could contain partial melt, rock that is not fully solid but not fully liquid either. A mixture of solid crystal and liquid silicate that interrupts wave propagation in a way that either end member alone would not. It could contain unusually iron-rich compositions, chemically exotic even by the standards of the deep lower mantle, where conditions are already extreme by any surface measure, or some combination of all of these. The honest answer, as with so much of the deep earth, is that the debate is not finished. But the most widely discussed possibility, the one that occupies much of the research into ultra-low velocity zones, is that some of them may contain partial melt, actual liquid rock pooled at the very base of the mantle, in pockets perhaps only a few kilometers thick, pressing against the roof of the molten iron outer core on the other side. If this is right, and it is a genuine if, then the ultra-low velocity zones are among the deepest reservoirs of melt anywhere inside the Earth. They would be pools of liquid silicate sitting at the contact between the solid mantle above and the liquid iron below, occupying some of the most thermally and chemically extreme real estate the planet has to offer, existing in conditions no laboratory can fully replicate and no instrument can directly sample. Their presence at the margins of the Large Low-Shear-Velocity Provinces is not accidental in the view of researchers who study them. The margins of Tuzo and Jason are exactly where the thermal boundary layer is most extreme, where the heat from the core is most intensely focused, where the conditions for partial melting of deep mantle rock are most likely to be met. The ultra-low velocity zones cluster there because that is where the heat is highest and the conditions are most unusual, and it is from these same marginal zones, from these same edges where partial melt may pool and exotic chemistry concentrates, that the plumes appear to rise. Think of the edge of one of the great provinces as a place of convergence. Heat from the core concentrates there, funneled by the geometry of the steep wall. The boundary layer is hottest there, most thermally unstable, most prone to driving upward motion. Small patches of rock may cross the threshold into partial melt, pooling in ultra-low velocity zones just above the core mantle boundary. And from these same margins, from these same zones of maximum thermal stress and minimum seismic velocity, buoyant plumes detach and begin their slow rise through hundreds of kilometers of solid mantle toward the surface of the Earth. The edge of Tuzo or Jason is not a place you could stand, for more reasons than the obvious one of inaccessibility. It is not a place with a clean line, a visible wall, a dramatic cliff you could photograph. In the way that seismic images render it, it is a gradient compressed into a narrower band than the surrounding mantle, a region where the seismic properties change more steeply than they do through most of the deep Earth. But within that gradient, within that compressed zone of change, the conditions are such that the planet does some of its most consequential organizing. The heat that has been arriving at the core mantle boundary for billions of years, conducted outward from the cooling iron core, finds at the edges of the two buried continents a set of conditions that gather it, focus it, and send it upward. And upward, through hundreds of millions of years, is where the story of the surface has been written. Every volcanic island chain, every great rifting event, every outpouring of basalt that buried a landscape and changed a climate and reorganized the roll call of species on Earth began somewhere deep. Not in the shallow crust where the magma eventually emerged. Not in the upper or middle mantle where the plume matured and travelled. At the bottom. At the edges of two enormous, ancient, chemically distinct piles of rock resting on the roof of a churning sea of liquid iron, 2,900 kilometers beneath the surface of a planet that, from the outside, gives almost no sign of any of this. The named hotspots, Hawaii and Iceland and Runyon and the Afar region, are the quiet ones. The ongoing ones, the ones that are producing their heat and their lava at a rate and a scale that is dramatic for a human observer, but manageable for a planet. The volcanic island chains and the geothermal fields and the rifting continents are the planet's steady-state expression of what its deep interior is doing. What the large igneous provinces represent, the Siberian traps and the Deccan traps and the dozens of similar events in the earlier history of the Earth, is a different scale of expression. The same mechanism, a plume or a cluster of plumes rising from the margins of one of the great buried provinces, but amplified, accelerated, or interacting with the particular thinness of continental crust, or the particular composition of the lithosphere in a way that allows the deep heat to reach the surface not as a sustainable trickle, but as a catastrophic flood. There is something unsettling about sitting with the Siberian traps for a moment, about allowing the numbers to have their full meaning. 252 million years ago. Before the first dinosaurs, before the first flowering plants, before the first mammals, as we would recognize them. Life had already been on land for 100 million years. The seas were full, the continents were configured differently, most of the world's landmass was gathered into the supercontinent Pangaea, which was just beginning its slow breakup. But they were populated, thoroughly and diversely, with a community of organisms as complex and as variously adapted as anything the Permian world could produce. And then, the Siberian traps began. Erupting at the margin of one of the two buried provinces, driven by a deep plume rising from one of those steep walls, the volcanism went on and on, releasing gases in quantities that the relatively stable Permian atmosphere could not absorb without fundamental change. The oceans acidified, the oxygen levels dropped, the temperature rose and then fluctuated. And the organisms that had spent hundreds of millions of years adapting to one set of conditions found those conditions changed faster than adaptation could follow. 66 million years ago, the Deccan traps were already in progress when the asteroid arrived. The sky above what is now the Yucatan burned. The darkness that followed was total in the weeks after the impact, and the food web that depended on photosynthesis collapsed almost immediately. The non-avian dinosaurs, dominant for over 150 million years, were among the casualties, but the Deccan volcanism had been underway for a period before the impact and continued after, adding its own atmospheric chemistry to an already catastrophic situation. And the deep source of that volcanism traces back through the motion of the Indian plate across millions of years, back toward the margins of Tuzo, the African Large Low-Shear-Velocity Province, sitting beneath the planet tonight, as it sat then. The edges of these two buried continents have been, in this reading, among the most consequential geographic features in Earth's history. Not the continents we live on, not the mountain ranges or the ocean basins or the tectonic plates themselves, but two invisible structures no human eye has ever seen, whose existence was not even suspected until the latter half of the 20th century, and whose detailed shape and chemistry and dynamics are still being worked out in research papers being written right now. The real tectonics of the planet, the oldest and deepest organizing principle of where the heat goes and when the planet erupts, may live not on the surface but in those two enormous piles of ancient rock at the bottom of everything. And still, even now, even with the mechanism named and the plumes traced, and the catastrophes associated, the edges of Tuzo and Jason hold something more. The ultra-low-velocity zones that cluster at those margins, those small, seismically extreme patches where the wave velocities drop by tens of %, where the rock may be partially molten, where the conditions are the most intense and the most exotic anywhere in the mantle, are still being discovered, still being mapped. New seismic datasets, new computational models, new arrays of instruments recording the trembling of the planet from earthquakes large and small, are adding detail to the picture of these marginal zones at a pace that was not possible a decade ago. The edges of the buried continents are the frontier within the frontier, the most extreme and least understood zone of a region that is itself extreme and poorly understood. When a researcher publishes a new seismic model of the ultra-low-velocity zones, what they are doing, in the most literal sense, is listening more carefully to the planet, taking earthquake waves that passed through the lowermost mantle and extracting from their timing and their amplitude and their shape a little more information about what those waves encountered 2,900 kilometers down. The image that emerges, the map of where the velocity drops are sharpest and where the anomalies cluster most densely, is always an estimate, always model-dependent, always subject to revision as new data arrives. But the picture it reveals, the two great provinces, their steep edges, the ultra-low velocity zones clustering at the margins like pools of something extraordinary, has become more robust, more consistent, more detailed with each generation of study. The broad outline is not going to change. What will change, what is already changing, is the resolution, the clarity of the edges. The understanding of what specifically makes the velocity zones so extremely slow, the question of whether those zones contain partial melt or iron-enriched solid, or something yet unnamed and still surprising. The planet keeps its deepest secrets slowly, but it keeps giving them up. So we have arrived in this long listening at the question that sits beneath all the other questions. The existence of the two provinces, that part is settled. The mechanism by which their edges focus and launch the planet's deepest heat, that part is becoming clear. But there is a third question, the one that researchers circle back to, with a mix of genuine scientific disagreement and something that resembles personal fascination. The kind of question you find yourself still turning over while driving or walking or lying in the dark before sleep. And that question is simply, where did they come from? How did two continent-sized heaps of anomalous rock come to be sitting at the very bottom of the mantle, 1,800 miles down, apparently stable, apparently ancient, apparently permanent on any timescale that human civilization can really imagine? There are three answers, three serious, debated, genuinely competing ideas about the origin of Tuzo and Jason. And in a field where settled answers are rare, it is worth sitting with all three, not to pick a winner tonight, because the science has not yet picked one, but because each of the three, taken seriously, opens a slightly different window onto what the planet beneath us actually is. The first answer is perhaps the most intuitive once you know how tectonic plates work. The surface of the Earth is not fixed. The ocean floor in particular is constantly being made and unmade, new crust forming at the mid-ocean ridges where tectonic plates pull apart, and old crust returning to the mantle at the subduction zones where plates collide and one dives beneath the other. That sinking oceanic crust is called a subducting slab. And for a long time the question of where it went after it sank was somewhat vague. It went into the mantle. It mixed back in. The planet recycled it, the way a river carries sediment and eventually deposits it somewhere downstream. But the mantle is not a simple mixing bowl. It is more than 2,900 kilometers deep, and it is not well stirred on human timescales, or even on geological ones. Research over recent decades has made it increasingly clear that subducted slabs, those cold, dense, chemically distinctive sheets of former ocean floor, do not simply dissolve smoothly back into the ambient mantle. Some of them sink all the way to the bottom. They arrive at the core-mantle boundary and they pile up there, the way sediment accumulates in the deepest part of a lake basin. Oceanic crust is chemically different from the mantle it sinks through. It is richer in certain elements, denser in certain ways, and it carries within it material that has been chemically processed at the ocean floor, altered by seawater, layered with sediment, transformed by heat and pressure as it descends. Over billions of years, plate after plate, ocean after ocean, these chemically distinctive sheets of former seafloor have been sent back into the Earth. And the proposal is that they did not fully mix. That enough of that material sank all the way and collected at the base of the mantle, building up over geological time into dense heaps of compositionally unusual rock. Under this view, the two provinces are the planet's deep compost heap. Everything that goes down eventually arrives here. The sunken remnants of oceans that no longer exist, former seafloors of Tethys and Panthalassa, and ancient ocean basins whose names are reconstructed from fossil evidence alone. All of it sent back down and accumulated, compressed and buried and preserved at the very bottom of the mantle in two great piles that have been growing, slowly and steadily, for hundreds of millions of years or more. Tuzo and Jason, on this reading, are Earth's archives, a record in dense and sluggish rock of every ocean that plate tectonics has ever consumed. There is supporting evidence. The density of the provinces, that few percent excess over the surrounding mantle, is consistent with what chemists and mineralogists calculate for the end products of deeply subducted and transformed oceanic crust, under the pressures and temperatures of the lowermost mantle. The locations of the provinces bear some relationship to the long history of subduction zones, where plates have been sinking for geological ages and where that material would logically accumulate at the bottom. The cold slabs that pool in the deep mantle as their own kind of graveyard seem, in some models, to form a ring around the hot provinces, as if they have been herded, pushed and squeezed by the cold, dense former ocean floors raining down around them, accumulating in the spaces not occupied by the cold slab material in the two great basins that have formed between the slab graveyards. Cold and hot, dense and less dense, pooling at the bottom of the planet in an arrangement shaped partly by the history of plate tectonics at the surface. The idea that the surface and the deep interior are in conversation, that what happens at subduction zones 5, 10, 50 million years ago shapes what sits at the core-mantle boundary today, is itself a remarkable feature of the picture. The planet is not simply stratified and separate surface events in one column, deep events in another. It is one circulation. Slow, yes, gradual beyond anything a human life can perceive, but connected, top to bottom, over time. And yet the subducted slab origin story has trouble answering everything. The provinces are not just dense, their seismic properties do not match perfectly with what models predict for recycled oceanic crust transformed under deep mantle conditions. There are discrepancies, arguments about whether the specific chemistry works out, whether the volumes add up, whether the timing is right. The subducted slab hypothesis is serious and well supported. It is also incomplete in ways that leave room for the second origin story and the third. The second idea is older, in a sense, and quieter. It proposes that the provinces are not the product of plate tectonic recycling at all, that they predate plate tectonics, or at least that their core material is primordial, that they are left over from the very beginning. From the time when the young Earth was a largely molten world, a magma ocean, and the rock of the planet was separating itself into different layers based on density and chemistry, the way oil and water separate in a bottle you shake and then set down. As that magma ocean cooled and crystallized, different minerals settled at different depths. Some material sank, some floated, some crystallized where it was, and certain dense, iron-rich, chemically anomalous material may have settled to the very bottom of the molten rock column, directly onto the forming core, and never left. On this reading, the two provinces are not recycled. They are original. They have been sitting at the base of the mantle since before the continents existed, before the oceans existed, before life existed, before any rock at the surface was even solid. They are older than the oldest mineral grain that geologists have found at the surface, which itself dates to about 4.4 billion years ago. The provinces, under this primordial model, would be among the oldest coherent structures on the planet. Older than anything you can hold in your hand. Older than anything exposed to sunlight or rain or biological chemistry. A remnant of the molten, churning world that preceded everything we call Earth's history. This is the version that produces a particular kind of stillness if you let it settle. There are things at the bottom of the mantle that have not meaningfully changed since before the first single-celled organism appeared, before the first mineral formed in a geological sense, before there was a surface to stand on. And they are down there right now, beneath the floor of the room where you are lying, beneath the sediment and the bedrock and the crust and the mantle above them. Patient and dense and ancient, beyond any real comprehension, the primordial view asks us to imagine a continuity between the very earliest Earth and the Earth of tonight. It asks us to think of those piles not as artifacts of geological process, but as survivors of the original formation of the planet. Witnesses, in the loosest possible sense of the word, to the moment the Earth became the Earth. The third origin story, and in practice it may not be entirely separate from the second, is that the provinces are neither purely recycled nor purely primordial, but some combination of both. That there is an ancient core to each pile, perhaps primordial material that settled out in the early magma ocean, and that over billions of years the subduction of oceanic crust has slowly added to that core, refreshing and growing the piles, feeding them from above. A mixed origin, part ancient and part continuously replenished, part original Earth material and part the recycled remains of ocean floors that have been coming and going at the surface throughout the long history of plate tectonics. This mixed view has a certain elegance. It does not require one mechanism to explain everything. It allows the provinces to be genuinely old at their heart, while still being fed and shaped by ongoing planetary processes. It is also, honestly, harder to test, because disentangling the primordial component from the recycled component in a pile of rock you can only study with seismic waves is an extremely difficult scientific problem. The mixed hypothesis may be the most realistic and yet the least falsifiable, which is its own kind of lesson about how science actually works, particularly when the objects of study are 2,900 kilometers away. But there is a fourth possibility that is different in kind from all three of these. It is not competing with the recycled slab hypothesis in the way a geological argument competes with another geological argument. It is operating in a completely different register, connecting the story of the buried continents to a story so large and so strange that it almost requires a pause before you follow it down. About 4.5 billion years ago, the solar system was young and violent. The inner planets were still forming, accreting from the dust and gas and colliding rock of the early solar nebula. The proto-Earth existed, but it was not the Earth you know. And then something happened. A body roughly the size of Mars, a protoplanet that has been given the name Theia, after the Titan in Greek mythology who was the mother of the moon, struck the young Earth in a colossal impact. The details of that impact are still debated by planetary scientists, exactly how large Theia was, what the angle of impact was, how much of the proto-Earth was disrupted. But the broad outline has been part of the scientific consensus for decades. The moon-forming giant impact is not a fringe idea. It is the leading hypothesis for how the moon came to be, supported by the chemical kinship between Earth rocks and lunar rocks, by the physics of what it would take to put the amount of mass in the Moon into the specific orbit it occupies by decades of modelling. What happened to Theia in that impact is the usual answer: it was shredded. Its material was mixed with the proto-Earth's outer layers, and the debris was ejected into orbit, where it coalesced over thousands of years into the Moon. That is the standard story. Theia was destroyed. Its material is distributed somewhere in the Earth-Moon system, thoroughly blended and unrecoverable. Except that a 2023 study, led by Qian Yuan and colleagues and published in the journal Nature, proposed something different. The researchers ran simulations of the giant impact and of what might happen to a particularly dense portion of Theia's mantle in the aftermath. And what they found in their modelling was that dense fragments of Theia's mantle could have sunk through the magma ocean Earth and settled at the base of the mantle, where they would have been dense enough to remain, to survive the subsequent billions of years of mantle convection without being remixed into the surrounding rock. Their argument, the two Large Low-Shear-Velocity Provinces, Tuzo and Jason, may not be recycled oceanic crust. They may not be primordial Earth material. They may be the surviving remnants of the mantle of Theia, the lost world that made the Moon. The largest structures inside the Earth might be the corpse of another planet. This needs to be held carefully, and Yuan and colleagues held it carefully. This is a hypothesis. It is supported by simulations, by modelling that asks what would happen under specific conditions, not by direct observation of the provinces themselves. The simulations are sophisticated, but they are models, and models make assumptions that can be questioned and refined. Other origin ideas remain competitive. The scientific community has not converged on the Theia explanation. It has noted it as a genuinely interesting possibility that is consistent with some of the known properties of the provinces and that deserves further investigation. So it would be wrong to say the buried continents are definitely the corpse of Theia. That is not the state of the science. But it would also be wrong to dismiss the idea as speculation without substance, because it comes from serious researchers using legitimate methods published in a serious journal. And it makes predictions that future research can, at least in principle, test. What it asks us to do, and this is what makes it so remarkable, is to consider that the planet beneath our feet has been carrying, since the very beginning, the remains of the world that died so that the Moon could be born. If the Theia hypothesis is correct, every time a mantle plume rises from the edge of Tuzo or Jason and eventually builds a volcanic island, what is erupting, at least in part, is material from the dead planet Theia. Hawaii would be, in the loosest and most indirect of senses, a monument to an impact that happened before the Earth had an ocean or an atmosphere. The Moon above you tonight would be the sibling structure to the two piles of buried rock below you, made from the same world, one sent up into orbit, the other sent down to the bottom of the mantle to wait. This is the edge of what the science currently holds, and it is right that you hold it there, at the edge, not as settled fact, but as the kind of idea that reveals how the past can be present in places you would never think to look for it. Now step back from the question of origin, because whichever of these explanations eventually proves closest to the truth, one thing about the provinces is not in serious dispute, and it is the thing that most changes how you think about the planet's deep time. These structures, however they formed, have been there for an enormous span of time, and they have not simply dissolved into the surrounding mantle. They have persisted. The mantle convects. It moves. At any given point in the mantle, the rock is in very slow motion, flowing under its own heat, rising where it is hot and buoyant, sinking where it is cold and dense, turning over in vast, sluggish circulation patterns that operate on time scales no human institution has ever needed to think about. The speed of that motion is commonly compared to the growth of fingernails, a centimetre or two per year, which sounds impossibly slow until you do the arithmetic. At 2 centimetres per year, a parcel of mantle rock moving upward from the core-mantle boundary to the base of the crust, a distance of roughly 2,600 kilometres, would take on the order of 130 million years to complete that leg of the journey. A full cycle, down and down again, could take several 100 million years or more. In those timescales, mountain ranges rise and are erased, oceans open and close. The continents you know assemble and break apart. The dinosaurs appear, reign for 160 million years, and are gone. And still the rock convects. Still the slow circulation continues, indifferent to what is happening at the surface. In that context, the survival of the two provinces is not obvious. If the mantle is convecting, if material is always in slow motion, why haven't the piles mixed away? Why hasn't the heat from the core gradually diffused through them and blurred their edges? Why are they still there? Still large, still apparently coherent, still detectable by seismic waves as distinct from the surrounding mantle? The answer is the density. A pile that is even a couple of % denser than the material around it will resist being stirred back in. It is heavy enough to sink back down whenever it gets nudged upward. It is heavy enough to stay pooled at the very bottom, while the less dense material around it rises and circulates past it. It is not perfectly immovable. Over very long timescales it can be nudged and reshaped, and there is debate about how much the provinces have shifted over hundreds of millions of years, whether they have been shoved by the arrival of cold slab material raining down from above, whether their shape has changed, even if their position has remained roughly constant. But they have not mixed away. The excess density is the anchor that keeps them distinct. Think of it like a bowl of honey with a heavy stone at the bottom. Pour water into the bowl and stir it. The water swirls and mixes. The honey distorts and circulates slowly, but the stone stays at the bottom. The stone is too dense to be swept up into the general circulation. The provinces are the stones. The mantle is the honey and water, in very slow motion, swirling past them. Over billions of years, the overall circulation continues. The provinces remain. There is debate, as there is about everything involving these structures, about how stationary they really are. Some reconstructions treat them as essentially fixed reference points, anchors against which the motion of surface plates and deep hotspots can be measured over hundreds of millions of years. Others argue that the piles are slowly mobile, pushed and squeezed by the cold slabs accumulating around them, perhaps gradually shifting their positions over very long timescales, perhaps changing shape even if not location. The truth is probably somewhere in between those two pictures, not eternal monuments, frozen since the beginning, but not freely churning heaps either. Something in the middle, persistent, ancient, resistant to mixing, but not completely static over the full span of Earth's history. What you can say with confidence is that they have been there, in roughly their present form and position, for long enough to have organized the planet's deep heat over the timescales during which the great, large igneous provinces erupted, the Siberian traps 252 million years ago, the Deccan traps 66 million years ago, and the many others before and between them. long enough to have been the source region for the mantle plumes that built Hawaii and Reunion and Iceland. Long enough that the planet's history of volcanism, its pattern of eruption and fire, cannot be understood without them. They are the oldest furniture in the room. There is one more thread to follow before this long listening comes to rest. A softer thread, less definitive, but perhaps the most quietly strange of all the things these buried continents imply. It concerns what sits just below them. The core-mantle boundary, the floor on which Tuzo and Jason rest, is the roof of the outer core. And the outer core is liquid iron and nickel, extraordinarily hot, in constant turbulent motion. That churning ocean of liquid metal, driven partly by the heat leaking out of the solid inner core below it and partly by the cooling of the mantle above, is what generates Earth's magnetic field. The mechanism is called the geodynamo, and it works because moving, electrically conductive fluid generates electric currents, and those currents in turn generate magnetic fields that loop out through the mantle, through the crust, through the atmosphere, and extend far into space on both sides of the planet. That magnetic field is not incidental. It is the shield. It deflects the solar wind, the constant stream of charged particles flowing outward from the sun, away from the Earth's atmosphere. Without it, over geological time, the solar wind would gradually strip away the atmosphere the way it has stripped away most of Mars's atmosphere. The magnetic field is, in a very real sense, one of the conditions that made the surface of this planet habitable for anything. And the two buried continents sit directly on the roof of the dynamo that generates it. The question that follows is not fully answered. It is a soft question, a research direction rather than a settled result, but it is a serious one. Does the pattern of the provinces at the core-mantle boundary influence how heat leaves the core? The provinces are anomalously hot regions sitting on top of the molten iron. Normal mantle material at the same boundary would extract heat from the core at one rate. The provinces, with their different composition and their different thermal properties, might extract heat at a different rate. And if the pattern of heat flow out of the core is not uniform, if heat leaves more easily from some regions of the core-mantle boundary than others, then the convective patterns inside the outer core, the very patterns that drive the geodynamo, might be influenced by the geography of what sits above them. The implication, handled very carefully because the chain of causation is long and not fully established, is this: Tuzo and Jason may be quietly shaping the magnetic field that protects the surface of the Earth. Not dramatically, not moment to moment, but over geological time. The pattern of where these buried continents sit and how they affect heat flow from the core might influence how the magnetic field is organized, where it is stronger or weaker, how it has changed over millions of years. It is a long chain of inference. The core physics is real. The connection to the specific provinces is suggestive rather than proven. But the idea carries a particular kind of weight. The same two structures that appear to be launching the mantle plumes that feed the planet's greatest volcanoes may also be, in some indirect and patient way, helping to sustain the magnetic shield that keeps the planet's air from being slowly blown away into space. Buried 1,800 miles down, visible to no one. Formed from unknown material of uncertain age, they would be doing two of the most consequential things one can imagine doing on a geological planet, deciding where the fires erupt and quietly influencing the shield that protects life. That is what it means to be the hidden architecture. There is one final thing to say before we let this go for the night, something that has been in the picture all along, but worth sitting with one more time, here at the end. The two provinces do not sit randomly distributed around the planet's interior. Tuzo is beneath Africa. Jason is beneath the Pacific. They are on roughly opposite sides of the Earth, not perfectly, not exactly antipodal, but close. Close enough that the near symmetry is itself a question that researchers have noted and attempted to explain. Why two? Why roughly opposite each other? Is the near antipodal arrangement a result of some deep dynamical principle, some organizing logic of planetary convection that drives the largest structures to settle into opposite hemispheres the way a spinning top stabilizes its weight distribution? Or is it a coincidence, or a near coincidence, a consequence of the specific history of subduction zones and slab accumulation rather than any deep symmetry? This question is genuinely open. There are ideas. Some researchers propose that the large-scale pattern of mantle convection naturally organizes into a rough two-cell structure, with upwelling concentrated in two regions and downwelling around them, and that the provinces occupy the two great upwelling regions. Others argue the positions are more historical accident than dynamical necessity, shaped by where subduction has been happening over the past hundreds of millions of years. No consensus. The honest answer tonight is that we do not know why there are two, or why they sit where they sit, in rough symmetry on opposite sides of the planet. And there is something almost fitting about ending here, not with a mystery manufactured for dramatic effect, but with a genuine one. An observation that the science has made and is still working to explain. Two structures, impossibly large, impossibly deep, possibly older than everything we can see or touch, facing each other across the interior of the planet in a symmetry that may mean something or may not. And that has been there, in the quiet dark of the deep earth, for longer than the surface world has existed in any form we would recognize. The largest continents on Earth are two that no one has ever seen. No satellite image has ever caught them. No human eye has ever perceived them directly. No sample of their rock has ever been held in a hand. They have been discovered entirely by listening, by the patient accumulation of wave arrivals at thousands of seismometers, by the slow construction over decades of better and better images from earthquake waves that passed through the deep earth and came out the other side slightly changed. We know they exist. We know they are vast. We know their edges are where the planet decides to launch its deepest fires, where the hot spots rise, where the catastrophic eruptions of the deep past seem to have originated. And we hold carefully the possibility that one or both of them may be the material remains of a world that no longer exists, that the corpse of Theia is what you are lying over tonight, down there in the dark, patient and dense beyond imagining, the most ancient resident of a planet that has been old for longer than the mind can really hold. There is something that happens when you learn this, when you really let it settle. The ground beneath you is no longer simply solid. It is not just rock and bedrock and mantle in some vague, undifferentiated mass. It has geography. It has history. It has structures that dwarf the continents you know, that predate the oceans, that were sitting in their positions when the first photosynthetic organism was changing the chemistry of the surface air. The planet is layered in time, the way it is layered in depth, and the deepest layers carry the oldest stories. And tonight, you are lying on top of all of it. The Atlantic or the Pacific, or a continent that has been assembling for hundreds of millions of years, is between you and the buried structures, but not so much between you as to make them distant in any meaningful sense. They are part of the same planet. The same heat that rose from their edges to build the island where someone, somewhere, is watching the light change on a volcanic ridge at dusk. That same heat from that same source is working its way up through the mantle below you as well. Very slowly. On a timescale that makes the whole of human history look like a single heartbeat. The fires are real. The buried continents that steer them are real. The uncertainty about where they came from is real. And the wonder at all of it, the genuinely vertiginous feeling that the planet is far more structured, far more ancient, far more organized in its deep interior than any of us were ever taught, that is perhaps the most real thing of all. If you find yourself thinking about this as you drift, about what it means that the largest things inside the Earth are two things with informal names honoring two scientists, names given not in any official atlas, but in the careful human tradition of scientific tribute, if you find yourself wondering whether the edge of Jason beneath the Pacific and the edge of Tuzo beneath Africa are, right now, in this moment, funneling heat toward columns of buoyant rock that will rise for hundreds of millions of years before eventually breaking the surface somewhere as a new hotspot. Somewhere that is not yet an island, not yet a mountain, not yet even a name. If that thought stays with you into sleep, let it. Some things are worth carrying down with you into the dark. We have travelled tonight from the surface of the Earth to a place no drill has ever reached and no eye has ever seen. 1,800 miles down to two buried continents resting on the roof of the liquid iron core. We have listened to the earthquake waves that slow as they pass through those provinces, and understood that the slowing is not a metaphor, it is a measurement, precise and reproducible, that tells us something real is there. We have followed the heat up the steep edges of those piles to the plumes that surface as Hawaii and Iceland and Reunion, and traced the edges further back to the Siberian and Deccan traps and the catastrophes that bookended the age of the dinosaurs. We have held three origin stories in parallel: the recycled graveyard of ancient oceans, the primordial residue of the earliest Earth, and the still contested but serious possibility that the two provinces are the surviving remnants of a world called Theia, the lost planet that gave us the moon. We have noted the near antipodal symmetry and been honest about not knowing what it means. And we have ended at the softest loop of all, the question of whether those buried continents resting on the roof of the geodynamo are quietly and indirectly shaping the magnetic field that protects everything alive on the surface above them. None of it was speculation made for drama. All of it is what serious scientists using real methods have found, or are arguing about, or are in the process of determining. The uncertainty is part of the science. The wonder is earned. There are questions you might find yourself wanting to carry into the conversation. What was it like, learning that the Earth has interior geography no map has ever shown? Is it stranger that those buried structures might be almost as old as the planet itself, or that we only found out about them in the last few decades? Does it change anything, knowing that the ground beneath you is in very slow conversation with events that happened before the first ocean existed? Whatever draws you, carry it. The questions are their own kind of company in the quiet before sleep. And for now, the buried continents are down there, as they have been for as long as the planet has been the planet. The mantle is convecting at its unhurried pace, moving rock that will not reach the surface in any of our lifetimes, or our descendants' lifetimes, or their descendants' lifetimes. The liquid iron of the outer core is churning, threading magnetic field lines out through everything above it, including you. The plumes rising from the edges of Tuzo and Jason are in motion, very slowly, toward surfaces that do not yet exist. All of it continues. All of it will continue. The deep earth does not need our attention to do its work, and the buried continents did not need to be discovered to be real. History will still be here in the morning. For now, rest.